Good morning, everyone, and welcome to our webinar on an introduction to ExSite and some of the new features in version 4. This morning we have Dr. Branko Damjanac, Principal Engineer with ITASCA Minneapolis. He has experience in the design and analysis of underground excavation for oil storage and waste isolation. He has been involved in the stability analysis of underground and open pit mines in both hard and soft rock. He has developed a 3D numerical model to simulate the coupled hydromechanical response of a fluid-saturated rock mass. He has been involved in a number of projects in petroleum, geothermal, and mining industries with the objective of design and operation optimization of rock mass treatment by fluid injection. So, Branko, if you'd like to start the presentation.
Thank you, Dave. Hi, everybody. Thank you for calling in. So the topic of today's webinar is the updates for ExSite version 4.0 that we just released last week.
So we will be having a Q&A session. If you have any questions, please just type them in to the Q&A dialog through the icon that's at the top of your screen. And then essentially at the end of the presentation, we will address any questions that you've posted. Thank you.
Okay, so the main objective of the seminar is to present new developments, improvements in ExSite version 4.0, but we would like to start with introduction and general background. So ExSite is a numerical software for simulation of treatment of the naturally fractured rock masses by fluid injection. In ExSite, rock mass is represented using a synthetic rock mass approach, and I'll a few more words about SRM. And then SRM is implemented in ExSite using Lattice numerical model. So this slide illustrates the synthetic rock mass, which has two components. So one, which is shown on the left side, it's representation of the brittle rock mass using packing, and in this case of the spherical particles, and we call it sometimes bonded block, a bonded particle model. And then the other component is basically the representation of the pre-existing joints, which are superimposed on this bonded particle model, and those joints can be represented in different ways. They can be a stochastic fracture network as the DFN, or they can be deterministic features like major fractures of faults. And the discontinuities in the SRM are implemented using a smooth joint model. I'm not going to go into details of describing smooth joint model. Those you can find in ExSite documentation available in the installation of the code or ITASCA website. So what are the advantages of SRM? And I'm talking here advantages not only when we use SRM and ExSite to simulate rock mass treatment by fluid injection, but generally in modeling of rock mass for different applications. First, it's a mechanics-based approach. SRM actually represents the actual dominant mechanisms of the formation and failure of fractured rock masses, which involve sliding opening of pre-existing joints and then fracturing of the rock bridges between those joints. If you use different approaches based on continuum mechanics, the failure of the rock mass is actually represented as a shear failure, which in reality is not correct mechanism. And then finally, in SRM, you can actually use the standard testing methods. You test joint diameter core to obtain elastic properties and the strength, or you test discontinuity. So in most of practical applications, then those properties obtained on typically tested samples have to be upscaled. And that upscaling involves typically different empirical approaches, which we all know are not general and not satisfying. With SRM, if we have correct representation of DFN and we have properties of these two components obtained on standard testing methods, the SRM actually takes care of the scale effect automatically. So what is lattice? Lattice is a quasi-random array of nodes and the springs in 3D. So the cartoon illustrates the lattice in 2D. One important thing to mention is that cartoon is a little bit misleading because it shows only one spring connecting two nodes, but in reality, actually, there are two springs. So one which is, as illustrated here, responding in a normal direction, but then there is also the spring that actually generates the force if there is shear deformation between two nodes. Nice thing about Lattice and its implementation in ExSite is that although Lattice deals with these properties of these components like springs, which really don't have true physical meaning, that means that those properties of those springs have to be somehow calibrated to match actual behavior of the material that you want to model, rock mass. In ExSite, that calibration is done internally automatically. So as the user of ExSite, you basically operate with parameters which we are used as engineer, which would be Young's modulus, Poisson ratio, unconfined compressive strength, toughness, and so on. So question is, why do we use lattice? Why don't we use, for example, something like which is equivalent to a particle flow code or PFC or some other approaches? One of the main reasons that we decided to use lattice and ExSite is greater computational efficiency. So with the lattice, you can view lattice as a kind of poor man version of PFC. So the main difference between general formulation of PFC and lattice is that lattice does everything, at least the implementation in ExSite in a small displacement, small strain. So there is great saving that as a result of the fact that we don't need to do any contact detection and so on, associated with large displacement and large strains. So in ExSite, we do coupled analysis. So lattice approximate the formation and the strength of the rock mass. It represents mechanical behavior of the rock mass, but then we also have a model to represent the fluid flow. So the first question is, what is the geometrical relation between lattice and the model that we use to represent the fluid flow, particularly fluid flow in the either pre-existing or induced fracture. So the cartoon kind of illustrates the relation between these two models. So whenever spring breaks or is basically intersected by pre-existing joint, we assume like there is a penny-shaped crack. And that penny-shaped crack has a diameter which is roughly equal to the lattice resolution. And in the calculation of the fluid flow, we kind of use these penny-shaped cracks as a reservoir. So we kind of store a fluid there and calculate the pore pressure changes and so on. But then if the penny-shaped cracks are within some distance tolerance, we assume that they are connected and that there is a pipe, basically, that then allows pore pressure dissipation during the simulation. So the fluid flow is, or the flow model is represented as a pipe network composed of these fluid elements or micro cracks connected by a pipe. When we say that ExSite is fully coupled hydromechanically, what that means is that the deformability of the fracture, the permeability of the fracture depends on aperture, and which on the other hand depends on deformation of the mechanical model. The fluid pressure acts as a loading on a solid model, affecting its deformation and the strength. So ExSite does the effective stress calculation. And then finally, there is this undrained effect of pore pressure change, even without any pore pressure dissipation as a result of solid model deformation and induced volumetric strain. So what are the advantages of ExSite compared to a number of other conventional codes that are used for simulation, let's say, of hydraulic fracturing? ExSite doesn't make any, in ExSite, we don't make any assumptions regarding the fracture trajectory. So the fracture trajectory is a part of the model solution. We don't assume symmetrical fracture with the two wings or anything. We don't assume that fractures are planar. So fractures can turn as dictated by the stresses and interaction between multiple hydraulic fractures and the existing joints. ExSite automatically resolve general interaction between multiple hydraulic fractures and between hydraulic fractures and the existing joints. And ExSite can simulate fracture propagation in heterogeneous and the fractured masses. So here, in the next few slides, I'll just go through summary of the ExSite capabilities. So ExSite has both Linux and Windows version. Linux version is typically used to take advantage of high performance computing centers. ExSite has a convenient, easy to use GUI that allows you relatively fast creation of the models, interactive use of the code. So we can preview the model during its generation, but then we also preview the result and manipulate them in a 3D. The models can be set up in local and global coordinates. The advantage of the global coordinates is that once we import, let's say, geometry of the geology or wells or whatever, that imported geometry can be used for multiple ExSite models. So we can move the model, within different parts of geometry, which is defined in a global coordinate. ExSite has many built-in rock types, but then the user can always set their own. There are different ways to initialize the model, particularly in situ stress with fluid pressure. I didn't mention in the slide also temperatures. And this initialization also includes capability to, besides having a relatively simple constant pressure or the pressure or stresses with a gradient, we also have capability to input complex initial flow pressure and stresses from let's say other 3D continuum codes, and that might allow us to basically import initial conditions which are basically affected by previous well production, like in modeling these parent-child wells. So there is observation that fracturing in vicinity or the existing wells which produced is significantly affected by perturbed stress and pore pressure fields. one of the main features of capability ExSite that we can explicitly represent the pre-existing joints, and we can represent hundreds, thousands of fractures. There are literally no limitation on how many of these continuities can be imported and included in the model. And we can, in ExSite, we can simulate arbitrary number of wells, injection points. We can represent different types of well completion, including perforation clusters, open hole completions, and perforation tunnels. And also, there is capability to generate synthetic microseismicity, which can then be compared with the field data and used for model calibration. In ExSite, we can simulate non-steady fluid flow in both fractures and in the matrix. Of course, there is interaction and continuity of the fluid between the joints and the matrix. Intention of using matrix flow in ExSite is one way to represent the leak off. But then we can also use what is kind of standard of conventional way of representing a leak off by oil and gas industry, which is Carter leak off. The fluid flow also includes capability to simulate proppant transport and a placement of fluid in the code can be Newtonian, but we can also represent power law fluids. We can also represent non-Darcy effects and pressure drops and the clusters. So in the reservoir scale models, of course, the detail of perforations cannot be explicitly represented, but we can still represent the perforation pressure drop in the model using the formulas, which are function of injection rate and the geometry of the perforations. ExSite has capability to simulate different modes of heat transfer, and that's one of the main features added to version 4.0. So we can simulate different modes of heat transfer, which are very much relevant during the process of circulation of fluid through the rock mass. For example, in case of applications to geothermal projects. So these modes, of course, include the heat conduction, but then also advection of the heat by fluid in a fracture and convective heat exchange between the fluid and the rock. And so these different models, mechanical, fluid flow, heat transfer, can be simulated separately, but then also we can simulate them coupled. And there are different modes of coupling. The most accurate one would be by basically syncing all these models, but we know very well that because of very different time scales of these processes, that for a number of applications, that type of coupling would be extremely inefficient. So we have actually different coupling modes that allows simulating these problems much more efficiently. And then some capabilities which are very convenient in terms of managing the simulations. Model can be saved and restored at different stages during simulation, allowing some kind of branching of the model, testing different conditions. Model can be run interactively. However, in the situations when the execution takes a long time, it can be also run in a batch mode where all simulation stages are predefined and then model automatically executes it. Unlike, again, for the purpose of having a simpler model, the code use actual units. It's not generic code like other ITASCA code where user needs to make sure that the units used are consistent. Actually, in ExSite, uses inputs for specific units. However, we have two unit systems, so the code can be set up and run using metric system or using oil field, typically units used by petroleum industry. There are different forms of graphical and file outputs. Code can use variable and adaptive resolution, meaning that the resolution within model can be optimized so that we use fine resolution in the area of interest, and then coarser resolution way towards the boundaries to basically save the model size. But then, really nice and unique feature of ExSite is adaptive resolution, which actually allows us to basically, in the problems, like, for example, multi-stage simulation from a well, the area of interest actually moves along a long distance, let's say from toe towards the heel of the well. So having fine resolution along the entire well would not be very efficient. So the adaptive resolution allows us to have fine resolution only around the stage which is currently active. So then when the simulation moves to the next stage, we basically remesh the model and then use the finest resolution around the stage where we are injecting in the next step of the simulation. Related to that is also easy setup of multi-stage simulation. There are capability of importing and exporting different formats and files, and exporting is particularly geared towards exporting results of ExSite simulation, like changes in permeability and porosity to reservoir simulators. So then can be used in different codes for, let's say, simulation of long-term oil or heat production. So what are the new features in ExSite 4.0, which is the main purpose of this webinar? First, we updated the GUI, so we optimized it for high resolution displays, improved the readability and formatting of all dialogues, improved scroll bars, which is allowing window resizing, auto-scaling, when moving between different resolutions. ExSite can use web license. And in terms of developments and improvements of the core of the code, we implemented the implicit solver for fluid flow analysis using Jacobi iterative method. And now I have a couple of slides to illustrate improvements of using in terms of speed gain using implicit logic. And then we implemented capability to simulate different heat transfer mechanisms, including advection by fluid and convective heat exchange. And associated with that, we have capability to conduct multi-stepping for heat advection, which is really convenient because it significantly speeds up simulation of heat advection, which in some of these simulations is probably the part which takes most time. We implemented a scheme for optimized simulation of THM processes driven by thermal diffusion in rock. So with this scheme, we can actually use the code to simulate the long-term processes of fluid circulation for the months or years, which are very relevant for the production phase of geothermal projects. And again, advantage of ExSite for this kind of simulation is that we can actually do this production phase in the model where we explicitly represent the discrete fractures and created hydraulic fractures, so without resorting to any upscaling. We generalize thermal boundary conditions, and that allows to make, let's say, simulate the effect of cooling of interior of the well on stress changes and the condition for fracture initiation from the open hole completions or from the perforations. And associated with this, also we have a sync logic that kind of allows to kind of simulate the heat production during geothermal projects. We optimize and improve the importing low pressure fields and the DFNs. These are kind of convenient things, and then improve the history, location selection, and reporting of history information. So I have a couple of slides to just kind of illustrate a performance gain, or in other words, the speed up of ExSite simulation that involved the modeling of fracture fluid flow. So not only speed up, but also the effect of implicit logic on the accuracy of the model results. So here, actually, this is work and example done by Christine. So we are looking at the simple problem of propagating a penny-shaped crack. So basically, we're looking at the fracture in a vertical cross section. We inject fluid for 20 seconds at the rate of 5 liters per second. The model is cube, 20 meters edge length, and 1 meter resolution. So use of implicit logic for fluid flow calculation is relatively simple. So before the implicit logic was implemented, the integration of the fluid flow model was done using explicit time step, critical time step. So with explicit logic, basically the explicit logic is not unconditionally stable. So that means you have to calculate the critical time step. So the way implicit logic works, a user just need to specify the time step multiplier, meaning, and that time step multiplier is basically applied on the critical time step of the explicit logic. Now, the implicit logic uses Jacobi scheme, which is iterative. So additional parameters which are used to when you specify the implicit logic are the convergence factor, which is basically relative error in a pore pressure between two successive iterations, and then also the minimum number of iterations that the iterative scheme will carry out, and the maximum number of iterations that the scheme will carry out. So these four pictures, and I apologize that they are not very clear, basically shows the contours of the pore pressures at the same physical time. And it shows the pore pressure, the injection cluster pressure history during simulation. So the chart scales are exactly the same. So I hope you will be able to kind of see that the injection pressure history looks very similar, and you can also see that the fracture fluid pressure contours look fairly similar. In the next slide, I'll actually show you the exact numbers in terms of comparison of the numerical results for the injection pressure history. But here you can see kind of visually. Now, these four plots are done for explicit simulation, which is a case where the time step multiplication factor is equal to 1, factor equal 5, 10, and 15. Now, at the bottom of each slide, we also report or show the computation time. So for this particular example, explicit simulation took almost 19 minutes. Exactly the same problem with time step multiplication factor of 15 took 1 minute and 21 seconds. So you can see significant speed gain. Now, here we provided two tables. One is done for convergence factor of 10 to the minus 4, which is a little bit less strict, and the other one is done for a convergence factor of 10 to the minus 6. And here we compare two things. One is the performance gain, which is runtime ratio. So basically, we calculate the ratio of the simulation time compared to the explicit simulation. But then we also compare the injection cluster fluid pressures at the end of the simulation for all those cases. So the injection cluster pressure give us some kind of indication of the effect of implicit scheme and time step multiplier on the accuracy, assuming that the explicit solution is the reference value. So we can see that. So clearly, the reason why the runtime ratio is not equal to time step multiplication factor is when we do implicit logic, it's iterative scheme. So basically, during that time step, we are iterating multiple times. So that's why the gain, for example, if we use a factor of 19, it's not 19, but somewhat less. But you can see also that there is error associated with using this implicit scheme and longer time step. So instead of 23.1, we have 22.3. So, and again, this is for the case of convergence factor equals to 10 to the minus 4. So I would say that this error as a result of using much longer time step factor is less than 5%. However, when we use stricter convergence factor, we pay a little bit price in speed gain. So now it's not 16 times, it's 12, but you can see that then actually the error in the results is much less. Okay, so before showing you an example problem of modeling of heat transfer mechanisms of the kind that you would expect during, let's say, geothermal project. I would like just to mention a few basic or explain some basic mechanisms regarding heat transport during fluid circulation in the fracture rock. So in this complex process, there are a number of different processes occurring at very different time scales. First, we have response of mechanical model, which occurs probably at the shorter time scale, which is associated with the wave speed in the solid. The next is basically time scale of the fluid flow, which also occurs at very fast or very short time scale. Considering heat transfer mechanism, we can identify few. So first, we have thermal advection with fluid flowing inside the fractures, and this is very fast process associated again or related to the speed of the fluid flowing in the fractures. On the other hand, thermal conduction in the rock mass. So this is the process of thermal front propagation from the fractures into the rock. Occurs at quite slow rate. So, and the consequence of that is relatively low thermal diffusivity of the rock mass. Typical thermal diffusivity for the rock mass is 1 in minus 6 meters square per second. So if you take how long it takes for the front to propagate for 1 meter, it's roughly 1 million seconds, which is, if you do calculation, approximately 10 hours. So there is a challenge how to basically efficiently and accurately simulate all of these processes. If we are simulating stimulation of the reservoir, where we simulate injection of the fluid at high rate, which is associated with relatively large pore pressure changes, then those two processes are driving the whole entire problem. And consequently, we are forced, if we want to do thermal coupling occurring in the same time as, let's say, hydraulic fracturing, we have to then carry out simulation where we tightly couple all these processes. Fortunately, as I mentioned, the heat conduction is very slow process. So for most of the problems of where we simulate hydraulic fracturing, the effect of thermal heat conduction and the thermal effects can be neglected, as I mentioned, because to propagate the thermal form for 1 meter, it would take roughly like 10 days. On the other hand, stimulation of these reservoirs takes place on much shorter, for much shorter time, approximately a couple of hours, or sometimes even shorter. So, however, if you are doing simulation of, let's say, fluid circulation, as we would do during, let's say, heat production, in that case, the entire process is driven by heat conduction. So in that case, we can actually assume that our mechanical model is continuously in equilibrium and our flow model is continuously in a steady state, and then basically run the model by simulating heat advection, executing heat conduction periodically to see how much the heat front propagates into the rock, and then reestablish mechanical equilibrium and a steady state corresponding to thermally induced stress changes and in the model. Another important challenge here is that basically at early times of, let's say, circulating cold fluid in the fractures, there is a very steep temperature gradient near the fracture wall, which would impose significant requirement in terms of mesh size. That then also would have significant effects on the simulation time. However, we resolve that problem, and that's again work that Christine has done by basically implementing analytic solution in the early times, so we can actually capture that gradient even by using a relatively coarse grid. Okay, so I'm going to demonstrate you basically a relatively simple example problem of different heat transfer problems similar that would occur, let's say, during geothermal projects, but then fully coupled with mechanical and fluid flow models. So this example is documented in more detail in an article that has been published with information which is listed at the bottom of the slide. So we assume that there is a pre-existing fractures with 50 meters radius and 0.5 millimeter initial aperture. We created the model of the size of 120 by 120 meters and height 50 meters. We assume that the rock and the fluid in this fracture have initial temperature of 300 degrees C, and then we inject at relatively low rate, something like half a barrel per minute, cold fluid at the location of the inlet, indication here in the slide, and we keep the zero pressure boundary condition at the outlet, and at the outlet we also basically record the rate of the production of fluid flow, temperature of the produced fluid, and in the end also the power and energy which are produced. So what I'll do, I'll open ExSite model. So here is the geometry of the model, which is shown in the sketch model. So if we go here to hydraulic fracturing tab, borehole. So basically here we specify the conditions of the fluid injection. So we have only one stage, and as I said, we inject, this is like one liter per second. Now, in terms of the initial conditions for a thermal model, we see that the initial temperature of the rock is 300 degrees C. Initial temperature of the fluid is also 300 degrees C. We assume that those two are in thermal equilibrium. And then temperature of injected fluid is 200 degrees C. Now, to simplify modeling of this problem, because we say, okay, the initial state is such that the aperture is 0.5 millimeters. We first run the model to achieve the steady state for the flow model. So we run the model sufficiently long to achieve the steady state. So how do we know that we have achieved steady state? So if we open a history of the, so basically we start injecting at the inlet, and we are monitoring the rate at the sink or the outlet. So if you look at the sink flow rate, so basically you saw we were injecting with defined injection rate of 1e minus 3. So once the production or flow rate into sink reaches 1e minus 3, we can be pretty certain that the model is in a steady state. And we can also see the contours of the pore pressure in the steady state. So basically here we are injecting, so this is injection pressure, here we are producing. So this is the sink fluid pressure. In the next step, we run the model to equilibrium, mechanical equilibrium, because running the model to this steady flow state, we created certain pore pressure field which is acting on the solid model. So we want to make sure that once we start simulating the circulation of the cold fluid, the model is in the mechanical equilibrium. So if we go here in the batch window where we specified all simulation steps, the next step is basically was running model to mechanical equilibrium. I'm not going to go there because of the time limitations. And then in the following step, after we reach the mechanical equilibrium, we carry out the simulation of the basically injection of a cold fluid, and we carry out these simulations using this optimized THM scheme, where basically we run the model where we simulate heat advection, and then periodically execute the conduction model to see the effect of basically exchange of heat between the rock and the fluid on cooling of the rock. And then also periodically, then as a result of these temperature changes in the rock, we equilibrate the model to see the effect of basically temperature change on deformation and change in apertures. And then finally, we also then run the model to steady flow. Now, all these steps are basically carried out automatically, and how they are carried out is actually specified basically here in this window in setup of the batch process. So basically, the way this thing is done, we save the state of the model every 12 days. However, the coupled simulation is carried out in such a way that every 6 days, we basically stop thermal simulation, which is advection and conduction, and then we run the model to mechanical equilibrium, running it for 5 seconds, and then we run the model to fluid flow steady state, running it for 30 seconds. So what I'll do now, I'll restore the final state. So I think this state corresponds to the state of the model after 1 year. So what we would like to see here, so for example, if I turn the sketch model again, maybe turn, okay. So for example, we would like to see how the temperatures at these history points evolve during 1 year. So if I go here, select the history, so we want to see the fluid. So there are temperatures of the fluid, but then there are also temperatures of the surrounding rock mass. Actually, what I will do is, instead of having contours of the fluid pressure, I'll actually show here first contours of the fluid temperature. So what you can see is, so we are injecting cold fluid here. You can see that the temperature around the injection point of the fluid is around 20 degrees. That's what we are injecting. And we are producing at this point here, you can see that the fluid basically cools down. And then there is this part which stays, which is where there is very little fluid circulation, and the temperature there stays more or less at the initial temperature. Now, we want to look at the temperature histories at these different locations. So So I'll go, this is history of point one, then we go at the inlet. You see the inlet temperature drops much faster. So these are then temperatures towards the sink. So yeah, so this is actually roughly temperature which is produced at the sink. Okay, so this is what's happening in a fluid. What are the temperatures in the rock? So we can contour those. So let's say if we put so in order to see, because now we're seeing temperatures on the outside boundary, so we need to make a kind of cross section through the fracture. So if I put it here, let's say maybe, so you can see then how the cooling front actually propagates from the fractures into the surrounding rock. What would be also of interest to see is how the cooling of the rock affects the deformation and the apertures. So I'll turn off these histories and let's say add the histories of the aperture. So again, let's go from point one inlet to. So you see this bumpiness? So that actually comes from this fact that we don't do this thing continuously. We run things for 6 days, then we equilibrate. So the changes in aperture happen only every 6 days when we basically equilibrate the model for thermal-induced stress changes and so on. And then maybe finally, what is really of interest is, okay, what is the produced energy? So if we can go here and say, so this is the produced sink power. So basically, initially we produce more. The energy is the integral of the power with time. So we can also have yeah, so the energy keeps increasing, but there is some trend because the power kind of goes down since the temperature also is decreasing. So I think we're kind of running out of time, and that's roughly what we prepared to present today. So if there are any questions, I would be more than happy to answer. If we run out of time, I would, I can maybe okay.
Great. Thank you very much, Branko. Thank you for your presentation. We do have a question. If anyone else has a question, please just click the Q&A icon at the top of the app and type in your question. If you prefer to speak, just raise your hand and I can unmute you. So we have a question. Do fractures propagate in preferential directions in anisotropic rock masses, for example, sedimentary or foliated rock?
Yes.
Yes.
Yeah. There is a capability to represent. We have properties which are dependent on the orientation. So we have capability to represent. We can represent anisotropy actually in two ways. We can represent it as a matrix anisotropy in a way where the properties of the springs are function of their orientation. But there's also a way to represent anisotropy, but by explicitly putting discontinuities. So depending again on a spacing, So
Great. Thank you, Branko. All right, I'll give a few more seconds if anyone has a question. Again, just type it into the Q&A or raise your hand. What are the differences between ExSite and mass flow? They both simulate fracturing and deformation of fractured rock masses. Has ExSite been used for capability assessment?
No, I mean, ExSite is the special purpose code just for simulation of, again, treatment of the rock mass by fluid injection. So, I mean, the logic behind ExSite, SRM, and Lattice can be used in whatever for different problems like capability and so on, but not with ExSite. ExSite it's not a general code like Flag 3D or it's a special purpose code just for these types of problems.
So ExSite, for example, is used in mining applications for preconditioning of rock mass.
That's correct, but not for capability.
Yes, then ExSite is a small strain model, so you wouldn't have large movements of material. So very different problems, two different product solutions. Great.
Yes.
All right, any other questions? Great, well, thank you everyone for joining us today. We will be posting the presentation and the recording of this webinar on our YouTube channel. Thank you, Branko.
Thank you.
And have a good day, everyone. Take care.